Hi everyone, I'm Professor Kelly. I'm going to be talking about data types, and this is a lecture for CSCI 308, Programming Languages Design. To start us off, let's take a look at this XKCD comic strip. Randall Munroe invites us to imagine a made-up programming language. In this language, if you try typing in 2 plus 2 in quotation marks, you get 4 in quotation marks. Well, that makes a certain amount of sense. You also get, if you do 2 in quotation marks plus empty square brackets, 2 in square brackets in quotation marks. All right, that's a bit odd. 2 divided by 0 is nan, or not a number. Well, that makes sense. But 2 divided by 0 plus 2 is NAP. What's going on here is that it has added 2 to the last character in nan, incrementing n to O and then P to create NAP. If we jump down to line 11, 2 plus 2 returns none, or line 13, where floor 10.5 returns an ASCII image of a 10.5 sitting on a floor. Randall Munroe's hypothetical language here invites us to think about what we expect to happen when we perform these operations. This is the question computer scientists have to consider when they're designing a programming language. So, learning goals from this lecture are, by the end of it, you should be able to define what a data type is, distinguish primitive from constructed data types, examine differences in data types across languages, and discuss the implications for code portability. A data type is a tool for communication. It allows the programmer to tell the compiler interpreter what you intend to do with the data. It determines how the data is stored, how the data is displayed, and what operations can be performed on the data. Data types are not strictly necessary. In Bash, for example, the Unix shell scripting language you're learning this week in lab and last week in lab, there are no actual types. For example, if you created a variable, let's call it A, and assigned it the value 2334, it's not actually an integer or a string. It's just data. You can add, subtract, or multiply. Let's add 1 to it, all right? We're going to get 2335. Well, that makes sense. But we can also treat it as a string and substitute characters. So let's substitute the 23 at the start for the letters BB. Well, we get BB35. So far, so good. But if we combine these operations, combine treating it as a string and treating it as arithmetic, we can get some strange results. For example, if we try adding 1 to BB35, well, what we get is B now equals 1. Does that make sense? Why does that happen? It is perhaps a somewhat unexpected result. So, for this reason, for the sake of clarity of communication between computer and human beings, many programming languages make use of data types. Java in particular uses fairly strict typing. Java's data types include booleans, which are stored with 1 bit and have the values true or false, and the operations and or not. Integers, which have 32 bits, and a range of values that can be represented within those 32 bits, ranging from negative 2 to the 31st to 2 to the 31st minus 1, and can be added, subtracted, divided, or multiplied. Doubles are 64-bit floating point numbers and can similarly have arithmetic operations performed on them. Java also has characters, which are Unicode characters represented using 16 bits, such as the letters on your keyboard, and surprisingly can also have arithmetic operations performed on them, which allow you to, say, advance from the letter A to the letter B by adding 1, or go backwards by subtracting 1. All the types seen on the previous slide are primitive types. Primitive types come with a language, do not need to be imported or written by you, cannot be constructed using the tools provided by the language. Conversely, constructed types typically either need to be imported in a library or written by you, or they can be created using the tools provided within the language. Generally, they're created using a type constructor. So, Java has arrays and objects as its constructed types. Objects, for example, can be created using a class constructor, and they can be operated on using the defined methods internal to the object. Arrays, on the other hand, one can measure the length of the array, and one can access specific locations in the array. So, how do we represent strings? Most languages support string literals, such as hello world in quotes. But how is the string stored? This varies widely across languages. In Java, strings are represented as objects. In MATLAB or C, they are arrays of characters. Similarly, in Haskell, they're lists of characters. In JavaScript, well, JavaScript couldn't really make up its mind. JavaScript represents them either as objects or as primitives. Let's take a closer look. So in JavaScript, we can do s1 equals quotes 2 plus 2, and this will be a primitive representation of a string. Conversely, if we do s2 equals new string 2 plus 2, here we're using a type constructor. We're invoking the string class and using its constructor to create a string object. For the most part, these two things are going to be treated the same in JavaScript. But if we use the eval function, an eval on s1 is going to give us 4, whereas an eval on s2 will just give us back 2 plus 2. So, are strings primitive in Python? Let's think about it for a moment. And strings are objects in Python, and objects can be constructed in Python, so maybe they're constructed. On the other hand, strings come with the language. You don't need to import strings from a library. And if you made your own string class, it would need to use an explicit constructor, like hello world equals string brackets hello world. Whereas in Python, you don't do that. You just go hello world equals quotes hello world. This suggests that even though they are objects, strings are importantly primitive to Python. So different languages have different primitive types. Python has booleans, arguably strings, as well as integers and floats. Java also has booleans. It does not have strings as a primitive type. It has characters. It has a bunch of different flavors of integer of different size, byte, short, int, long, and it has two different flavors of floating point number, float and double. C has characters, but does not have booleans. The C++ adds booleans later. It has short int, long int, which are pretty much the same types of integers that Java has, but with slightly different names. It also has float, double, and long double, meaning that it has a third type of float for even bigger floats than Java. So let's talk a little bit about sizes. Some languages guarantee the sizes of types, and some do not. Some compiled languages, such as C and Fortran, allow you to set the size of the types in the compiler options. As a result, the size of the type can actually change every time you compile if you use different options. Here's the compiler options for changing the real and double to both be 64-bit in Fortran. Every compiler's defaults can be different, and in fact, if you have an old 32-bit Windows or Linux computer, it may have smaller default sizes. For example, in C, A long double might be 64 bits on a 32-bit machine versus 128 bits on a 64-bit machine. Relative sizes are still, however, enforced. For example, in C, floats always have to be less than or equal to doubles in their size, and doubles always have to be less than or equal to long doubles in their size. While the ability to modify the size of data types is quite powerful, it can cause disasters when you try to port code. Changes in hardware can lead to changes in data type sizes by default and can lead to code failures. An infamous example is the Ariane 5 explosion in 1996. The rocket blew up shortly after takeoff, and it turned out the cause of this was it reused software from the Ariane 4 rocket. And the Ariane 4 rocket had different computer hardware. This caused well, basically a rounding error that caused the rocket to explode. Languages with consistent data type sizes, such as Java or Python, are more portable and less likely to cause the rocket to explode. All right, learning goals. We talked about what a data type is, and it does two things. It communicates how to use the data. It communicates between the programmer and the interpreter or compiler. It tells the interpreter or compiler specifically what values, operations, and storage of the data in a language is basically allowed. We've learned how to distinguish primitive from constructed data types, which, if you're thinking about it and you're like, I'm not entirely sure, well, there's certainly a little bit of room for debate. But basically, primitive is built in, whereas constructed is made using the language. We've examined differences in data types across languages. Basically, languages vary in both the kinds and implementation of data types. Finally, we've discussed the implications for code portability. Fixing how the data types are stored in a language improves portability, even though it constrains the programmer. All right, that's all.